Welcome. My name is Ali Yahya. I am the Director of IonFlux Sales and Services at Fluxion Biosciences. Today I'm going to present to you hERG assay development on the IonFlux system using Giga-seals and Ensemble recordings. First, some background. Fluxion was founded in 2005. Its headquarters is in California with worldwide distribution, winner of 5 NIH grants, 2 R&D 100 award winner for BioFlux 200 and IonFlux in 2010. 4 main products, BioFlux 200 and now Easy, BioFlux 1000, IonFlux 16, and IonFlux HD. Let me give you a brief overview of the IonFlux 16 and HD. The IonFlux system is an automated patch clamp system released in 2010. What makes it unique is that it is based on completely different liquid handling strategy. This strategy allows it to have plate reader simplicity. The IonFlux 16 has 16 amplifiers, while the IonFlux HD has 64 amplifiers. What makes the system unique is the recording plate. It is a standard SPS format with 96 well for the 16 and 384 well for the HD. The bottom of the plate is replaced by an intricate laminar flow system with integrated compound delivery and recording. This is a schematic of how the plate laminar flow system looks like. The recording plate has 2 traps with 2 independent recordings, 8 different compounds or concentrations, with independent conduits allowing no mixing, no cross-contamination, no pipetting, no electrode compound contact. In fact, the design of our microfluidics was featured on the cover of Assay for August 2012. We also have a paper featured in this issue. I will be showing a slide later on that paper. The operation of the device is quite simple. The IonFlux 16 has 8 different experimental procedures. The HD has 32 experimental procedures. Simple preparation to start. Simply fill up your solutions and your different concentrations. Once the plate is inserted, a pneumatic interface with the recording array will seal on it. With continuous flow, cells are introduced and trapped. All solutions keeps on flowing. 20 cells are trapped in ensemble plates, and a single cell is trapped in single hole plates. Once the cells are trapped, seals are formed, and then whole cell patch clamp is achieved. Recording with fast and successive compound additions and continuous compound washing. No pipetting for compound delivery, allowing simultaneous application and recording across the plate. This parallel application is what makes the system extremely fast in collecting data from the multiple recording sites. In fact, 32 experiments are completed in a matter of minutes, allowing 500 compounds with 8 points dose response to be completed in few hours. Okay, now shifting gears a bit, the human ether-go-go-related gene. This gene encodes the protein Kv11.1, which represents the cardiac current IKR. Modulation of this channel is believed to be directly related to QT prolongation, LQT2. This representation below shows a simplistic model of the activity of the different major currents in the cardiac action potential. IKR acts on the repolarization phase, so a decrease in the current would affect the AP duration and hence would cause LQT. Another important fact to mention is the gating of the channel. It can exist in 3 different voltage-sensitive states: closed, open, and inactive. From closed to open is a slow process, but from open to inactive is quite fast. It is due to this gating mechanism that we need to investigate the channel via a 2-step process. 1 to activate the channel, and 1 to measure the current tail as the channel is closing. So let's look at hERG recordings on the IonFlux systems. Initially, most of our recordings were done with ensemble plates or modes, and I'm going to explain that a little bit more further. This slide shows current voltage relationships of hERG using ensemble recordings on the IonFlux. The activation and tail currents were recorded via a 2-step voltage protocol with activation at +50 and tail at -50 millivolts. Panel B shows the current in response to increasing activating steps. Panel C shows the current in response to increasing deactivating steps. This very clearly shows the inactivation of the current. Panel D shows hill fits of a few compounds. This data was published in this paper. For digital reprints of all the papers mentioned in this webinar, please contact me directly later on. We also looked at the current voltage relationships using a similar voltage protocol. A shows recordings of tail currents as a response of changing activating steps, with C measuring the steady state current and D measuring the peak current. B shows the recordings of tail current as a response to changing the activating or second step, with E showing the tail current versus voltage. In both C and E, you can see the effect of the inactivation of the channel. The app note also displays a table of some standard known blockers on hERG. The pharmacology compares well with literature. Please take note that due to the continuous flow of our system, compounds with high log P, which are considered to be problematic in most APC systems, do not have problems on the IonFlux. For example, terfenadine with a log P of 6.5 can be quite problematic to use. However, on the IonFlux, it still shows an IC50, which is quite in accordance with literature. Another great feature of the IonFlux system is temperature control. Considering that the recording and pneumatic interface comes from the top, the bottom is kept free. Hence, we can have a heating plate right under the recording plate. This gives us the most accurate temperature control with positive feedback and rapid changing. In fact, we can record this. This is a plot of the R open hole versus time as we are changing the temperature. You can see that the resistance is dropping as the temperature increases, but most importantly, the changes here are happening within approximately a minute. We tested temperature-dependent pharmacology on a few drugs. This is an experiment with erythromycin. When the temperature was 22 degrees, the effect of increasing doses of erythromycin were not extensive. In fact, it did not make much of an effect until 1 millimolar concentration. However, when the temperature was raised in the same experiment to 35 degrees, the current became larger and the effects were more pronounced. You can see the dramatic effect below. Panel B shows the difference in control current between 22 and 35 degrees. Panel C shows the effect of 1 millimolar erythromycin at 22 degrees, and panel D shows the same concentration effect at 35 degrees. This table shows the difference in the IC50 for some drugs, and as listed, erythromycin becomes much more potent at higher temperature. So does sotalol, but not fluoxetine. More information can be found in the app note. The effect of temperature on hERG current voltage relationship was also studied in this paper by the Novartis group, with a shift in the IV as can be seen. The benefit of the IonFlux system is that it is one of very few APC that can do experiments like these without too much effort. In fact, temperature control and or temperature sensing is a matter of a simple software click of a button. In 2001, we released a new plate design that allowed single-cell or Giga-seal recording to be conducted on the IonFlux. The difference is that instead of recording from 20 cells in Ensemble mode, we record from 1. This allowed us to record the seal resistance when a single cell is patched and to achieve Giga-seals recordings. Please note that Ensemble plates are also most likely patching cells in Giga-seal format, but due to the parallel nature of the resistance recording, it is quite difficult to measure Giga-seals in Ensemble mode. With that said, Ensemble recordings are really designed for increased success rate due to the 20-cell redundancy, while single cells are designed for the highest quality. However, considering that the 20-cell redundancy is not there in single hole, it became apparent that a more stringent hERG assay is needed in order to achieve acceptable success rate and recording quality. In our assay development, we use two cell lines, ChO-hERG Plus by BESIS, also known as ChO-hERG Duo, and Millipore Precision ChO-hERG. We did many modifications to the traditional assay, but here are a few notes. We used these standard solutions with a few important notes. We made sure osmolarity is around 305 outside and 295 inside. We adjusted with sucrose addition. We kept the cells in 30 degrees incubators for at least overnight before the experiment. This step allowed a boost in expression of the current. We standardized on detachant for lifting the cells with more than 10 minutes incubation time. We allowed the cells to rest for at least 30 minutes in serum-free media before the start of the experiment. And we used around 8 million cells per plate, or 3 to 5 million per ml. We also standardized our voltage command to a simple square step. With a holding at minus 80 millivolt, we step down to minus 100 to allow membrane resistance measurements, then up to minus 50 to measure the leak component. Then activate the current at plus 20 for 5 seconds, followed by a step back down to minus 50 for 4 or 5 seconds, and then back to holding. Interstep was 15 seconds. This protocol produced good definition of the current tail, which was used for all peak current measurement. The peak tail was subtracted from the initial leak current measurement at the initial minus 50. We also noticed very large variability in current expression with both cell lines and on both systems, IF16 and IFHT. These are actually superimposed tracing from different cells at the same time. However, we noticed that more than half of the cells expressed current higher than 200 picoamp. The left panel shows all of the current seen on a test IonFlux 16 plate, while on the right, we see all the current seen in only 1/4 of the IonFlux HT plate. So in effect, if we are seeing here around 11 cells showing current above 200 picoamp in the IonFlux HT, then we should expect around 44 cells producing good data on a single plate. Next, we looked at longevity or stability of the recordings. It is very important to have stable recordings so that a dose response can be easily quantified. We were able to achieve very stable recordings for more than 20 minutes. Please note that considering the speed of the IonFlux with regard to liquid movement, there is not much need to extend experiments to more than that. However, we did test up to 45 minutes in many cases and found pretty good stability in recordings. However, for our assay standardization, we focused on 20 minutes. The panels below show control and the addition of verapamil, demonstrating the definition of the dose response with clear steps in response to the addition of the drug. So what constitutes then an assay success criteria? We need a sustained tight seal resistance and a measurable current amplitude with minimal rundown. We looked at the Giga-seals over time and noticed that we could achieve more than 800 megaohm seal resistance in at least 50% of our cells. We also noticed that the seal is sustained for at least 20 minutes, showing only a slight decrease in seal quality. So more than 50% of the cells showed sustained seals above or equal to 800 megaohm. We then measured currents and noticed that we can measure at least 200 picoamp of current in more than 55% of our cells, also showing good current definition and minimal rundown for more than 20 minutes. So here, around 60% of the cells showed greater than 200 picoamp of current. These two conditions are very important since although we do get variability in our recordings, we can safely say that greater than 50% of our recordings should show a seal resistance of at least 800 megaohm and a current amplitude of at least 200 picoamp. The sustainability of recordings should also be at least 20 minutes. This, of course, does not mean that the seals are going to be all below 1 gigaohm. In fact, our measurements showed that most seals were around 1.4 to 1.5 gigaohm. This also means that if you want to accept currents that are less than 100 picoamp, then your criteria would become looser. We also did IV curves and measured the steady state current, here clearly showing the inactivation of the current, and the tail IV, here clearly showing the reversal at around minus 77. We then looked at some pharmacology to compare with our Ensemble recordings. First was verapamil, showing an IC50 of 0.19 micromolar with N equals 16. Surprisingly, more potent than our published table with the Ensemble recordings. Then we tried terfenadine, which, as I said, is a very difficult drug to use. It showed an IC50 of 0.013 micromolar, also more potent than our Ensemble data. We also tried this assay recently with some customer cell lines at the customer site. These cells showed around 75% success rate with at least 100 picoamp current and more than 50% showing sustained giga-seals. We also tried the same assay, but with Ensemble plates and got 100% success rate. So this better assay is not only good for single-hole plates, but also for Ensemble plates. This is the last slide, actually. And the last slide shows cisaproid pharmacology done on the customer cells, again at the customer site, showing a more potent IC50 than our Ensemble data. So in summary, with the development and optimization of the hERG assay, the IonFlux system is well suited for hERG characterization and screening while capitalizing on major capabilities, including the use of single and Ensemble plates with no system upgrade, best-in-class temperature control, and unique microfluidics allowing continuous flow. Thank you very much.